Hello everyone and welcome back to a new session for Computer Science 2, LTU Summer 2022. Today we are at chapter 18. We're going to discuss what are linked lists. Before we start, I would like you to take a look at this email that I received from LTU. LTU Course Evaluation Deployment Alert. Dear, you are receiving this email because my course, Computer Science 2, is part of the Summer 2022 online course evaluation process. They are telling me I need to communicate the importance of these questionnaires to your students in an effort to achieve high response rates. So please do contribute, and all the emails that you received about this survey, do answer the questions and do the survey in hope that we improve the course or give credit for good work. If I'm doing good work, then please give credit, and if there is anything that you don't like, also give your feedback. I would like to take your attention about that the emails has been sent to students, and I will be receiving emails for non-participants. So if someone didn't participate yet, I will keep getting email that some student didn't participate yet. And you need to know that for the results reports that I and my administration receive after the final grades are posted. So that's what I need you to know. So don't be scared or afraid. I'm not gonna know the names of the students, and I'm not gonna know until the end of the semester. This happens every semester. So basically, after the end of this semester, I'm gonna receive the results, and even when I receive the results, it's not gonna show the students' names. It's going to show me the feedback and how students participated in that survey, but nothing personal, and I don't take anything offensive. With that being said, let's move on to our course. So as I mentioned, today we're going to talk about linked lists. What are linked lists? Linked lists are dynamically allocated data structures, and they are linked together in memory to form a sort of a chain. The best way to explain it is to draw it. So let me go to Paint. In linked lists, we're gonna have a struct. We're gonna build our own struct. I'm gonna call it my node. Now this struct has this code. It has some value that it holds. It could be int, double, it could be more than one, like 5 values, whatever. So I have a section for carrying the package, the cargo, and then I have a section which is a pointer to another node, and we call it next. So if you want to imagine, this is my node. I have a section for a cargo, a value, or values. And I have a pointer to next node. This pointer can carry a null value, or it can carry an actual valid value, which is the address of the next node. So if I want to draw a simple linked list, my linked list would look like this. I'm going to have a node that has some value. Then it points to a new node that also has a value and points to a node that has value, then points to a node that has some value the last node is gonna have null. So m next, this m next of last node is equal to null pointer. And if you remember from C strings, in a C string, the difference between a C string and string class is that in my C string, I'm going to have characters, and those characters are terminated by null. For example, let's say it's my name. If I have a C string, which is an array of characters, so I'm going to have K, H, A, L, I, L, K, H, A, L, A, F, and then I'm going to have the null terminator. In order to figure out the size of this array or this C string, what is the method that I follow? The method that I follow is I start from the first character and I start by initializing size equals to 0. Then my algorithm would be, hey, first character, are you null? If you're not null, then I increment size and I move to the next character. Hey, current character, are you null? If no, then I increment size and move. I keep iterating. Sorry. I iterate as long as the current character is not null. As long as the current character is not null, I move forward. Once I reach null, then I break out of my loop, and then I return size. By the time I reach a null terminator, then I have size incremented all the way from the beginning till here. So it will return the actual number of characters in that C string. When we come to linked list, in a similar fashion, in a similar logic, the way or the method or the algorithm or the approach to determine the size of a linked list is by starting at the first node. And then I ask first node, hey, first node, do you point to null or do you point to a valid node? If your m next is not equal to null, that means I can keep moving forward, and that's called traversing a linked list. So, hey, first node, do you point to a node or do you point to null? If you point to null, then I break out. That's it. Because if it points to null, then this is the last node. As a matter of fact, just so I don't confuse you, let's do it like this. When I write the code, it will make more sense to you. So all these point to valid nodes except the last node. The last node points to null. So in order to traverse a linked list, or in order to determine the size, which is also traversing. So determining the size is traversing. If I want to display all the values, it is traversing. Ooh, excuse me. So if I want to set the values, I need to traverse. So in any operation on a linked list, I need to traverse. The way to traverse a linked list again is by checking if m next equals to null. If m next equals to null, then the current node I'm on is the last node in the linked list. If m next is not null or it's not equal to null, that means it points to a valid node, so I can move forward. Now, when it comes to code, you're gonna see that, let's do it in green. You're gonna see that there is a fixed pointer called mhead. This mhead does not change, and we do not reassign it any value. If we lose mhead, which is a pointer that points to the beginning of the list, anytime we lose the value of mhead, we lose the entire linked list. If I lose the pointer to mhead, then I can't traverse the linked list. If mhead, which points to the first node, is lost, then I can't reach first node. From first node, I can't reach second node because I couldn't reach first node, and so on and so forth. So if I can't reach the first node, or if I lose the first node, I lose the entire linked list. And you're gonna notice that I'm gonna have also another pointer that starts, and I'm gonna call it current. This current pointer, so two important pointers beside mNext. mNext is internal to each node, but from outside these nodes, the way that to control or to manage this linked list, I need two pointers, one that points at the beginning of the list and one that points at the node that I'm currently on. When I start traversing at the beginning of the traverse, current would be equal to mhead because both pointers would be pointing at the first node. So both pointers carry the same memory address. So the first task to traverse a linked list is by setting current equal to mhead. I tell my program I need a pointer to a node, and this pointer to the node to a node equals to mhead. Now that current points to the first node, I can access first node by dereferencing that pointer. Remember, when I dereference a pointer, I access the value. So when I dereference the current pointer or the pointer current, I'm able to access the cargo of it. I'm also able to access mNext. Once I'm done with my task on the first node, whether it's to read the data or to set the data or to display the data, once I'm done, I can tell this node, hey, is your mNext equal to null? If your mNext equal to null, then I should not move forward. Otherwise, if your mNext is not equal to null, then I would like current to be equal to your mNext. That means if mNext points to this node, then current becomes equal to mNext since they both point to the same node. So if this node is at address 1, for example, and remember, linked list is not sequential in memory, it's associative. That means this node is not in particular on the same block with all the rest of the node. They aren't continuous in memory. This could be in memory address 1. This could be on memory address 5. This could be on memory address 2. This could be on memory address 100. This could be on memory address 67. Now, mhead is equal to 1 or carrying 1. So the address that mhead is carrying is 1. Why? Because the first node lives in memory address 1. When I start, I set current equals to null. So current at this point here would be equals or carrying 1. Now the first node here, although that the node as a whole, the node as an object, the node as an object lives in the address 1. It's carrying a cargo and it's carrying mNext. mNext would be 15. Why? Because the next node lives, oh, sorry, 5, not 15, because the next node lives in 5. So mnext equals 5. The address of mnext is 5. The address of mnext is 2. The address of mnext is 100. The address of next, the address of next is 67. And here, the address of mnext equals to null. Null. This node is a valid node. It lives in address 67. It has a cargo, but mnext equals to null. That means this is the last node. So if I go back to traversing as an algorithm or as an approach, I start by telling, hey, I need a pointer to a node, and I would like this pointer to a node to be equal to mhead. So now it is carrying 1. Let's remove these. So now current is equal to 1. So both mhead and current are pointing to the same node. Once I access and I'm done with whatever task I have, whether it's to read or write the cargo data, then I ask this node, current node, hey current node, is your mnext equal to null or is it something other than null? In this case, it's something other than null. Then I tell my code, I would like current as a value to be equal to whatever the first node or the current node mnext is. So I can do it in code using this code. So I can say current equals current mnext. When I do this operation, current becomes, instead of 1, it becomes 5. It becomes 5 because mnext is 5 and the next node lives in 5. So now current becomes equal to current mnext. Whatever current mnext will be set in current. So both of them, both this node's next and my current pointer will point at the same memory address. They both point at memory address 5, which is the next node. Then I can repeat the task, whether it is to read or write the cargo. Once I'm done, I can ask, hey, current node, is your mnext equal to null? If not, then I would like current to be equal to current mnext. So once I execute this statement, then it becomes no longer 5, now it becomes 2. Now that it became 2, it's now pointing to the next node equal to this pointer. I can keep doing this until I reach the point where, hey, current node, is your mnext null? If your mnext null, then done. I can break out of my loop. I'm done traversing that loop. So this is the concept behind linked lists and traversing the linked list. And we have 4 main operations. There are 3 basically, but the 4th one is traversing. If you know how to traverse, you can do a lot of things. So the main operations are to append a node. Append means add at the end. Let's say I have a linked list of 3 nodes and I would like to add a new node at the end of it. Append, insert a node. So I would like to insert a node at specific position. For example, I have this node, this linked list, 5 nodes, and I would like to insert a node here. I would like to insert a node here. That means I need to break this chain and should tell this node to start pointing at a new node and then tell the new node to point at this node. So basically, I inserted, and this is the advantage of linked list over other containers. Remember in vector, when we said it's sequential, that means every time you need to insert a value, all the rest needs to be shifted to the right because we need to maintain the continuity in memory. However, in linked lists, all nodes stay in place and then I can insert. This stays N2, this stays in memory address 100. This gets created once we call insert. So this gets created by calling the new. So we're gonna receive some memory address from the pool and it's gonna live in that memory address. For example, 119. If I wanna insert again, I'm gonna insert a new node here again that will live maybe at 206 and then break, tell this to point here, tell the new one to point to next and move on. And the last important operation is to delete. So insert, delete. These are the three important operations. Of course, to append, I need to traverse. To insert, I need to traverse. To delete, I need to traverse. So the fourth operation we can say is to traverse. And we're gonna call it in this example, display. Means iterate or traverse the entire linked list and display its data. We're going to assume that the cargo is only one variable. So display means in our session, traverse the entire linked list and display the values of each node. Each node has a value, one value. So 4 operations we're going to learn today. Okay, so for append node, I'm going to receive, as I mentioned, I'm going to receive a value. I'm going to need to traverse my linked list to add this node at the end of the list. Now I'm going to have 2 cases. In each of these methods, I need 2 cases. One case for what if my linked list is empty, and the other case is what if it's not empty. How do I check if my linked list is empty or not? I go back to my drawing. Remember mhead points to the first null. In this case, mhead is carrying the value 1. So if mhead is carrying some value, that means my linked list is not empty. Otherwise, if mhead is carrying null, that means my linked list is actually empty. So the first case is if my mhead equals to null ptr, this is one case, else the other case. And in order to guarantee that mhead is going to be equal to null if the linked list is empty, I'm going to set mhead to be null in my constructor. That means when someone creates an instance of my class, mhead is going to be equals to null. That means that instance is empty. So if mhead is null, that means it's a empty linked list, else I need to traverse to add to the end. But first thing first, when someone passes me this value, I need to prepare a node. I need to prepare a node that will be added to the list, whether it's empty or not. So I'm gonna say I would like a struct, call like L input. We're gonna call it input. Now L input, let's do it as a pointer. Now L input to value is whatever the value that I received. And even if I don't set mNext is equal to null based on the default constructor of the struct. When I come to my node, anytime someone constructs a node, which is this line, then mNext is equal to null pointer. If this confuses you, we're gonna be consistent by doing a constructor. In this constructor, mNext equals to null PTR. So anytime someone constructs a node, mNext will be set to null pointer. We can do mValue equals, for example, minus 9999, just so it's not a junk. So I need a pointer to that node, or it can be a node. It's based on your reference. Whatever you prefer, it's based on your preference. Whatever you prefer, whether you want it as a pointer or as a node, as long as this task is successful with no logical errors. And at this point, I'm gonna set it as a pointer. So I prepared a node that will be added to the list, whether it's empty or not. In case mHead is equal to null, means my linked list is empty, then I'm gonna say, okay, mHead, you are no longer null, you are now L input. mHead is a pointer to a node, and L input is a pointer to a node. This new node becomes head. So if I want to draw it, let's take all these out. Save. When someone creates an instance of my class, mHead will be equal to null point. When someone calls append node, the first thing that I did is I created a node and I said, okay, this is the cargo, and next is null. Then I went ahead and checked, hey, mHead, are you equal? And let's assume that this lives on the address 70. I go back here and I say node equals new node. When I execute this line, then the compiler is gonna go grab some address and say, okay, here you go. Here is the address. Now this is L input. L input is a pointer to a node and is carrying the value 70. The value here is whatever the value we receive when we call that function. So L input is carrying 70. Now in my if statement, the first case is empty and then the else is not empty. So in the if statement, if it is actually head, I'm telling it, okay, I want mHead to be equal to L input. What did this do to me? mHead equals to L input. This set mHead to be 70. So now it's no longer null. mHead becomes equal 70, means mHead point the same way an input is pointing to. So this null or this node becomes my list. Because it was an empty list, then the new node is the list. So now I'm gonna draw it here. This is how my linked list at this point looks like. or actually when we execute the code, I'm gonna draw the linked list in front of you. So this is the idea behind the first section of my task. If mhead is empty, then L input becomes mhead. So mhead points to this new node. Otherwise, if mhead is not empty, then first I need to traverse the linked list. How do I traverse the linked list? First, I prepare a copy of the head. Remember, you do not change mhead. If you change mhead, you lose the entire list. So I'm gonna say, I would like L current, some current pointer, to be equals to head. So if I wanna go back to my example, at this point, this becomes 70 if the linked list is not empty. If the linked list is not empty, then current becomes whatever mhead is pointing to. Then I'm gonna say, while L current slash, or not slash, arrow, mnext is not null, that means I can move forward. Remember in append, right now I'm in append. In append node, I need to traverse the entire list and then add the new node at the end of the list. So in order to traverse all the way to the end, I'm gonna say, while current mnext is not null, I would like to move forward. So if current mnext is not null, I would like current to be that not null. Then it's gonna go again. Hey, right now I'm at current. Hey, current, is your mnext null? If it is null, it will break out of the loop. If it's not null, then it will move forward. So this basically moves forward all the way until I reach current mnext equal to null. When I reach current mnext equal to null, that means current is the last node. So when I reach, when I break out of the loop, that means current mnext equals to null is true, right? This loop will not break out unless this statement is true. So I'm gonna tell current, hey current, your next is no longer null. Next is no longer null. Now it becomes input. And this is why, based on your preference, if you choose to have it as a pointer, then this is straightforward. If you choose this to be just a struct, a new struct, then you're gonna have to add the address of it. You're gonna say, okay, I have a struct and I would like mnext to become the address of that struct. But I recommend that you follow this because the book does it this way. I do it this way. Most and many people, developers do it this way. So to be standard, we're gonna use it as a pointer. And that's basically it for append node. It's either empty, then L input becomes mhead, or it's not empty, then I need to grab a current, traverse my linked list. Once I reach the end, then the last node points to the new node. And remember, since new node mnext is null pointer, then I'm good. Means next time I iterate using this, it's gonna be valid because the node that became last node, its mnext is null pointer. So next time I iterate, I'm gonna detect the end of the linked list based on this status. Okay, so save. I'm gonna take this out, save. Now let's test it. Let's go to main. Main is the driver program. I'm gonna say I would like an instance of list. Now, when I execute this statement, it's gonna have mhead equals to null. Then I'm gonna say, hey list, I would like you to add 1, to append 1. Then I would like you to append 2, or let's do 3 because we want to insert. So later we're gonna insert 2. Hey list, I would like you to append 5, and then let's run it. So this line has been executed. If I hover my mouse, I'm gonna see that mhead is null. That means it's an empty linked list. Then I'm gonna step into with the F11. Step into. I receive the value 1. Then I'm gonna say, okay, I would like a new node. Notice when I create a new node, the constructor has been called for this struct. The value is 999 and next is null. Then I'm gonna say, okay, the value is no longer 999, it's now 1, whatever I received, and next, I'm just being safe, I'm setting it to null. Then I'm checking, hey, is mhead null at this point? Yes, it is null. Okay, then the new node becomes mhead. Now mhead is a pointer that carries this value, and inside this value, I have the node that carries a cargo equals to 1, and its next is null. And that's it. Now on the next iteration, so let's draw it while we are executing it. So now I have mhead in green pointing to a node that is carrying the value 1 and null. This is my list at this point. Save, or not, no need to save. I'm gonna go back to my program. Then I'm gonna append again. Prepare the node. Here it is. Value is 3. Value is 3, and its next is null. Hey, mhead, are you null? No, at this point it's not null. It's carrying this address and it ends in 230. So I'm gonna go here and I'm gonna say mhead equals 230. So this node lives in the address 230. When I say this is gonna fail, if mhead equal null, this is false. Mhead is not equal null. Mhead equals the address that ends in 23. So it's gonna end up in the else statement. I'm gonna say, okay, I would like a new pointer that is equal to head. So notice it ends in 230. So I'm gonna go here. I'm gonna say, okay, current equals 230, or let's not put it here, current, so we can delete it later, which is equals to this pointer. So they both mhead and current point to the same memory address. They are both the value 230. Then I'm gonna say, hey current, is your next equal to null? In this case, yes, it is equal to null. So I'm gonna say it will break out. So I'm gonna say, okay, hey current, now let's prepare the node because we forgot. Let's prepare it here. So this node is carrying the value 3 and is living in the address 0F0. So 0, 0, F, 0. And this is null, and both are null at this point. So I'm telling it, hey, current, this is current. You see your M next is null. Yes, M next is null. Here it is. It's no longer null. It's no longer null. Why I can't increase? I would like to increase. Okay. So it's no longer null. It is now whatever the value L input is, which is 0F0. So now this is 0F0. That means it's pointing to this node. Done. So now this is my linked list. It's a node pointing to a second node, and the second node is pointing to null. Now I'm gonna append a third node. So again, go in, prepare a node. Let's prepare a node. Here is my node. It has 5 and it points to null. Hey, I'm head. Are you null? No, I'm not null. I'm equal to 230. Okay, then I would like to prepare current that is equal to M head. So here is current. Both are pointing to the first node at this point. Hey, current, is your next equal to null? No, my next is not equal to null. My next is equal to 0F0, which is the address of this. Okay, then in that case, you see that next 0F0, I would like you to be equal to it. So now go back. So now current is no longer pointing here. It is now equal to 0F0. So this is 0F0. That means it's pointing to this node. Okay, hey, 0F0. Is your next null? Yes, my next is null. That means you're the last node. Break out of the loop. And I would like you to start pointing to this node that ends in 640. So now this current next is no longer null. Now it is 640. And it's meaning it's pointing to this. So now my linked list is basically this. This is my linked list. It's a list of 3 nodes where the first is pointing to the second is pointing to the last, and current can be removed. It's not dynamically allocated, so I don't have to release it. And as a matter of fact, if I release it, I lose this node. So I'm good. This is it. If I hover my mouse, I'm gonna see that M head has the pointing to node with value 1, and its M next is pointing to a node with value 3, and its M next is pointing to a node with the value 5, where its M next is pointing to null. So this is my list: 1 to 3 to 5 to null. So this is for appending a node. Now we come excuse me. Now we come for inserting a node. So let me collapse this and come to my insert node. In this case, if I go back here, let's say I want to insert here. Let's say I want to insert 4. In order to insert 4, I need to keep track of the previous node. because I'm gonna iterate right from here. Basically, I'm gonna say, hey, is this where I need to insert? No. Okay, go. Is this where I need to insert? No. Okay, go. Is this where I need to insert? So every time I'm going, I need to keep track of the previous. Why? Because I'm breaking this chain. And since it's only a forward linked list, maybe I forgot to mention, but it is in the topic later, in the book later, there are types of linked list. We have doubly linked list, we have circular linked list, and we have forward linked list. This is forward linked list. I can only move forward. So once I break this link in order to insert a new node, I can't move back to the previous node. So that's why every time I move forward, I need to keep track of the address. So if I'm checking if I need to insert here, the previous is null. When I move forward, the previous is 230. If I move forward, the previous is 0F0. If I move forward, the previous is 640. I'm not worried about next as much as I'm worried about previous because I have access to next. If I'm at this node, I have access to next, but I don't have access to previous. So every time I'm at a node and I need to move forward, right before I move forward, I need to reserve this value. I need to know where is the previous node living in memory. With that being said, I'm going to prepare a node called L new node. This is basically equivalent to L input. So I'm going to call them new node. So new node, new node, new node, new node, new node. So I need one for the new node that is going to be inserted. And I need one that is called alcurrent to traverse. This is equivalent to this node. As a matter of fact, this can be, if I want to be consistent, this could have been declared here equals to mhead. Yep. So to be consistent, I have L node, new node is new node, L current node is equal to mhead, and I need a previous L previous node. Initially it's null, meaning right when I start, the previous is nothing. There is nothing previous. I'm at the beginning of the list. So right when someone calls insert, before I start traversing, previous is equal to null. With that being said, back to the two cases. If mhead is null, and I can check it by saying like this. That means, is this null or not? If mhead is null, then it's an empty, else it is not empty. If it is empty, then mhead equals to the new node. But I forgot to set the value. So L node equals, I can pass it here. This is default. This is a constructor that receives an int. And this equals to a value. So now I can go back to append. Instead of doing these two lines, I can say it's a new node and give it the value. I just added that constructor. So new node equals a value. This is not confusing. If you are confused, pause, play back, go back 1 minute, and notice I have a default constructor that sets m value to -999, and I have an overloaded constructor that receives the value. So in append, once I say I need a new node, I'm giving it the value. So now this new node has a value, whatever I received, and I'm next equals to null. Similar fashion here. Al current is mhead is constant. It's not gonna change. No function is gonna change it. So I'm safe. And L previous node is actually null pointer. So now I covered this case. If my linked list is empty and someone is asking to insert, then mhead points to this new node. The new node becomes the list. Otherwise, I need to traverse. So L current is mhead. Now, I need to traverse based on two conditions. I need to, because we assume it's sorted, right? It is sorted. So I need to traverse, I'm gonna do it in blue. I need to traverse based on two conditions. One, the first condition is I did not reach the end of the list. The second condition is as long as the value is less than the input, meaning if someone wants to insert the value 4, then I'm gonna start iterating. Hey, are you less than 4? If yes, move forward. Hey, are you less than 4? Yes, okay, move forward. Hey, are you less than 4? No, okay, stop. If you're not less than 4, then this is where I need to insert. I need to insert just before you. I have previous, I have the address of previous, and I am at current. So I can break the chain, insert, and stop, terminate. If I keep going, for example, this is the condition, right? The condition is less than. So I need this condition, the less than, or I didn't reach the end. For example, if someone wants to insert the value 7. So I'm gonna traverse. Hey, are you less than 7? Yes, okay, move forward. Hey, are you less than 7? Yes, okay, move forward. Hey, are you less than 7? Okay, move. I can't move forward. We're the end. So I need two conditions. As long as it's less than, and as long as we didn't reach the end. Because if we reach the end, you need to insert right there and then. Or if you reach the not less than, I need to insert right there and then. So in the else statement, while L current, just like we did before, M next is not null, and while the value of the current value of the current is less than. So as long as it's less than, move. I need you to move. Yep. So if that's the case, I need to do just like I did earlier. L current node equals L current node M next. However, before I change this value, I need to preserve it. So L previous node is L current node. Now that I preserved this value, I can change it. Now that I have this preserved, I need to change, then I can change it. This way, when I break out of this loop, I have access to current and I have access to previous. So when I break out of this loop, I need to check for two things. I might break out of this loop when previous node is still null, means someone is inserting to an empty node, to an empty node, or to a node, to an empty list, or to a list with only one node. So in that case, if L previous equals to null, I need to do one thing. Otherwise, I need to insert after the previous. So I either need to insert after the previous, or I need to insert before all other nodes. So if al previous is actually null, else, so if al previous is actually node, then head becomes the new node. And meaning I need to insert, yeah, meaning the new node becomes the first node. So let's say this is, for example, 1.5, and I'm inserting 1. If I'm inserting 1, that means head should point to the new node, and then the new node needs to point to current. So L new node next equals to L current node. This is one case, or I'm inserting just like I did in this example. So I need to insert, for example, I'm inserting 4. I need to insert between previous and current. So what I can do is I can say, hey, previous, I know that your next, if I'm inserting here, right? I know that your previous is, your next is 640. I know that you are pointing to this node, but I need you to stop pointing to this node and start pointing to the new node that we created, which is 4. So LPV next equals to L new node. Notice how variable names are very important. I don't need to check, oh, which one is the one I'm inserting. Just by using variable name, this is enough documentation. So hey, previous next, I need you to start pointing at the new node, and then hey, new node, I need you to start pointing to current node. This is where I'm at. I would be here. When I execute, you're gonna see it. With that being said, yeah, this is it. So notice why I'm checking for null, because if previous is null, I cannot access next. This will crash. If previous node, I need to do this task, right? We agree that I need to do this task. I need to tell previous to point at the current or at the new node, and tell new node to start pointing at the current node. But if previous is already null, then if previous is null, then this statement will crash my program. I cannot access a null. I can't access with an arrow a null instance. So this is enough. Let's execute it, and let's display it while executing. Yep. And we're gonna have a new values for the addresses because it's a new execution. So we can do like this. Yep. And we're gonna take these out because we're gonna add different ones. So let's execute these 3, and then I'm gonna say, hey, list, I need you to insert 4, for example. Then hey, list, I need you to insert 1. Let's insert 1, and let's tell this to be 2. So I have 2, 3, 5, and then I'm gonna attempt to insert 4 and attempt to insert 1. Save, run all the way to insert, because I know that append works. We already tested it. So now my list is Head is 4EO. So head is 4E0 or O0. So 4E0. And next, so this is the 2. And next, so 2, next is 5D0. So 5. Yeah, of course it's not O because we don't have O in hexadecimal. 5D0. So 5D0. And this is now 2, not 1. 2. And next, so this is 2 is at 5D0 and 3 is pointing to 490. So this is 490, 490, yep. And this is no longer null. It is 490. And this is 5D0. Yep. So now I'm going to attempt to insert 4. Let's go with F11. New node is with the value 4, and next is actually null. Our current node is going to be equal to head, which is 5D0, correct? 5D, oh, 5E or 5D? 5E0, sorry, here it is. 5E0. So 5E0. So current is 4E0. 4E0, yep. Then previous is null. So now I need a new one called previous. And at this point, it's equal to null. So here is current. Current is at 4E0 and previous is null. Hey, I'm head. Are you null? No, I'm not null. I'm 4E0. Okay, then go to the else statement. Then I'm going to check. What is my checking? My checking here is, hey, current node, is your next null? No, my next is not null. Okay, is your value less than 4? Yes. Okay, then move forward. With moving forward, I'm going to say to previous, hey, previous, you are no longer null. You now equal to 4E0 because that's current. And hey, current, you are no longer 4E0. You are now 5D0. 5D0 because that's what current is carrying as M next. 5D0. Okay, pretty cool. Next. Hey, al current. Hey, FD0. Is your next null? No. Okay. Is your value less than 4? Yes. Then move forward. Same. Now previous is 5D0 and current becomes 490 because current is carrying M next equal to 590. Next. Oh, well, I forgot to wait. So now I'm at 490, which is here. Hey, 490, is your next null? Yes. Okay, then break. And it happened that both conditions failed, but I only need one of them to fail. One of them to fail is enough to stop and insert. But it happened in this case that both of them failed. Next is actually null and value is not less than input. So this is where I need to insert with blue. I am at current and I have access to previous because I reserved it. Here it is. Previous is 5D0, current is 590. This link needs to be broken. So I'm going to prepare a node. I'm going to prepare a node here. We already prepared it, but I forgot to draw it. So 4, and it has null. Null. So, hey previous, are you null? No, I'm not null. Previous is 5D0. Okay. Go to hey previous. Hey previous, hey 5D0. Here is it. Here it is 5D0. I need your next to stop being hey 5, hey 4, 5D0. You are carrying value 3 and you're pointing to 490. I need you to stop pointing to 490 and start pointing to the new node. That means this link has been broken and now it points to new node. What is the value of the new node? It is 580. So this lives in 580. So this now became 580. And I need to tell the new node, hey, your next is not null, right? Here. Your next is no longer null. I need it now to point at 490 to carry 490. That means you point here. So I inserted this node. Now this is my linked list. My linked list now goes from 2 to 3 to 4 to 5. I inserted a node correctly, successfully. Continue with the execution. Go. Done. I inserted a node. If I hover my mouse now, I have head, which is carrying 2, then 3, then 4, then 5, and it's the last node. I need to insert another one, F11. Go. Same thing. Prepare a node and prepare a previous and stuff. So let's move these here. Head is still at 4E0. So let's prepare a node with red. This node is carrying 1 and null. So hey, head, are you null? No, I'm not null. Okay, to the next. Hey, current node, I am current node. This is current node. Current node is equals to the head. So this is 4E0, and this is null. I just started null. So hey, current, I'm at the while statement. Hey, current, is your next equal to null? No. Okay, is your value less than the input? The input is 1 at this point. So is your next null? No. Okay, is your value less than the input? Fail. So it will break out of the loop. When it breaks out of the loop, L previous is actually null. So I can't access its next right away. No. What I'm gonna do is I'm gonna tell head, hey head, you are no longer pointing at 4E0. I need you to start pointing at a new node. So now mhead, we broke this, and now mhead points to new node. New node lives in 800. So 800. So mhead becomes 800. And then I can tell new node, hey, new node, I know that your next is null because you're a new node. I know that your next is null. I need you to start pointing at current. What is current? Is 4E0. So now, this is the previous head, if you want to call it. So now, current, oh, sorry, the new node is carrying 4E0. That means it's pointing at this node. So now my linked list is 1, 2, 3, 4, 5. This is my linked list now at this point. Go, 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 done. L list, mhead is 1, 2, 3, 4, and 5 is null. So this is my linked list. Continue, done execution. Now we're gonna go for for deleting a node. So I'm gonna tell it I would like, hey, a list. I would like to delete the node, for example, 2. And go to delete. If I look at my display, which is this is my linked list now. So I'm gonna get rid of the unneeded stuff. Oh, we're gonna have to redo the addresses, but we don't have to at this point because delete is simple. Let's say I want to delete what? Which one? Which one we said we want to delete? 2. If I want to delete 2, basically what I need to do is I need to traverse while checking, hey, are you 2? Are you the one that needs to be deleted? Yes or no? So I'm gonna go with blue. I'm gonna start with traversing. Hey, are you the one? No. Okay, move forward. Are you the one? Yes, I am the one. Okay. So I need previous to stop pointing at you and start pointing at your next. So, hey, current, are you the one that needs to be deleted? If yes, give me your next. Release the memory. Tell previous to start pointing at preserved or reserved next. Very simple. Also, I have 2 cases. Is it empty linked list or not? If mhead is null, do nothing. If mhead is null, means that the list is empty. You can't delete a node from an empty list. Else, if that's the case, we need to prepare the same stuff. So I need a node called current, which is current node, which is equal to mhead. And I need a previous. I need to keep track of previous. Previous node equals to null ptr. So hey, mhead, is this an empty list that we are dealing with? If yes, return. Else, it's not an empty list. If it is not an empty list, then I need to check, hey, al current node, if. So hey, al current node, is your value equal to the one in question? Are you the one that I need to delete? If yes, then I need al current node to start pointing to current node next. Meaning, give me your next. Okay, reserve next. Give me your next, then delete Amhad. If you wanna, if you're confused, I'm gonna do it like this. Hey Amhad, okay, you're not an empty linked list. Are you the one that I need to delete? If yes, then give me your next, release yourself, release the memory, then the new head is al current node, basically. Otherwise, if you're not the one, then I need to look for the one. Why I need these? You might be wondering, okay, why do I not just iterate? Because again, I can't access using the same code. I cannot do the task for previous equals to null and the previous not equal to null with the same piece of code. I cannot write 3 lines of code that handle both cases if previous is null and previous is not null. This is the case for if previous is null, and then this is the code for traversing and previous is no longer null. So, hey first node, are you the one? If you're the one that I need to delete, I don't have a previous, so let me release you. Else, it's not the first one, so previous is not gonna be uh, um, previous is not gonna be node. So here I need to traverse. So traverse while, and I also have 2 cases. The cases are, okay, I traversed all the linked list and I couldn't find the node to be deleted. So while al current node is not null, and um, al current node value value is not the number in question. So as long as I'm not out of the bound, as long as I'm not out of the linked list, and as long as I didn't find the value, move forward. So L current equals L current node next. But before I do this, I need to preserve it. So preserve the value, then change the value. I'm gonna break out of this loop in 2 conditions. I'm either out of the linked list, means I reached the end of the linked list and I couldn't find the node to delete. It doesn't exist. I have, for example, 135 and someone called the code wants to delete number 6. Well, I reached the end of the list and I'm out of the list and I couldn't find the list. So in that case, if I didn't find the list, I don't need to do anything. However, if I break out of the loop because al current node is equal to a value, because al current node and value is equal to value, that means I need to delete it. So in order to check, I need to check, hey, am I out of the scope or not? Because if I keep doing this at the last node, if I do this loop and at the last iteration, L current node M next equals to null. And I'm setting L current node to be null. So when this executes at the very end and I come to this case, it's gonna break out of the loop. So when I break out of the loop, L current node will be null. I cannot access null. I cannot do anything with null. And if it is the case, I don't need to do in logic. I don't need to do anything because I reached the end of the list and I couldn't find the value. So You can say, for example, something like this, if it helps you understand. If al current node is null, then just return, do nothing. I don't have to do anything. Else, it's not null. So if al current, if I reach this code, and al current node is not null, that means I broke out of the loop because of this statement, not because of this statement. So if I break out of the loop because of this statement, that means L current node M value equals to A value. So I need to delete it. So I'm going to say, hey, previous node, your next is now L current node next. Just like I did here. Right now I'm at 2, right? In this case, in here, I broke out of the loop because I found the node with the number in question. The number in question is 2. So I reached this node. Hey, is your value equal to a value? Yes. Okay, previous. I need your next to become current nodes next. So it becomes like this. Hey, previous, I need your next to become L current next. What is L current next? FD0. So this becomes FD0, meaning this. And I need to delete 2. So delete L current node. Point. This is it. This will do it for me. So start all the way to delete. So what's my list? Again, it is 1, 2, 1, 2, 3, 4, 5. And I'm trying to delete 2. So go. Hey, are we dealing with an empty list? No. Okay. Is the first node the one that we need to delete? No. 1 is not value. Okay, iterate. Is current node null? No, current node is not null. At this point, it's equal to head. Okay. Is current node value not equal to the value? Yep, it is. So move forward. It's not. This is not the one we're looking for. So move forward, but keep track of previous. Hey, current node, are you valid? Yes, I'm valid. Means I'm still within the linked list. Hey, al current node value, are you not equal to value? No, this will fail. Okay, so it's a match. I found it. L current node and value is the value in question. So am I in a valid linked list? Yes, you are. Okay, then tell previous to start pointing at next and delete current node. Notice when I hover my mouse now, it is 1, 3, because 2 has been deleted, 4, 5. So 2 has been deleted. Now let's try to delete the first. Let's try to delete. We can do the first node, and we can try to delete a non-existing node and see how it will behave. It will help you understand. So let's stop and break here. So delete the first node. Go, go, go. Are we dealing with an empty list? No, we are not dealing with an empty list. It's 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. Okay, is mhead value the value in question? Yes, it is. Okay, preserve next. Next is 2. Delete mhead. Now mhead is deleted. Tell mhead to become current node. So now mhead is starts with 2, then 3, then 4, then 5. So 1 has been deleted. See, 1 has been deleted. Continue. Well, I didn't mean to continue. I needed to stop here. So we deleted 1. Go. List is has mhead. Hamad is 2, 3, 4, 5. So 1 has been deleted. Now I'm gonna try to delete a non-existing item. Are we dealing with an empty list? No. Is the first node the one that we need to delete? No. Okay, traverse. Hey, current, are you null? No. Hey, value, are you the one? No. Okay, move forward. Hey, current, are you valid? Yes. Are you the one? No. Move. Hey, are you the one? Are you valid? Yes, I'm valid. Are you what we are looking for? No, I'm not looking what we are looking for. Move on. What's current node now? Current node is 5, so this is the last node. Are you the one we're looking for? No. Okay, previous becomes the 5. Then current node becomes null. So, hey, are you valid? No. Okay, then stop. We reach the end of the list without finding the node in question. Is current node equal to null? Yes. Okay, then do nothing. No need to do anything. We can't delete an item that doesn't exist. With that being said, let's do the destructor. Display, you know how to display. You know, at this point, you know how to traverse. So list dot display list. How do I display? I just iterate. So I have node current node equals to mhead. Then I'm gonna say as long while current node is not null ptr, while I'm within the linked list, I need to see out current node value and L. Now that I displayed this, I need to move forward. Current node equals current node next. So let's display the list and on append. Let's display the list again on inserting. Let's display after deleting both. So let's add bunch of new lines to determinate or to differentiate. So C out and L and L. Every time I call this function, we're gonna have 3 new lines. Run. Run. So when I appended 3, 2, 3, 5, then I inserted 2 nodes, the 4 and the 1. So now it becomes 1, 2, 3, 4, 5. Then I deleted 1 and 7. So 1 has been deleted, 7 doesn't exist. The last thing you need to know about this is destructing the node. So this is my linked list, right? 1, 2, 3, 4, 5. I deleted the 1, but let's assume I didn't delete. In order to delete, I'm gonna move this here. In order to delete while traversing, I'm gonna start with mhead. If I delete just mhead, means I'm releasing only this node and the rest of the list is still in memory. And that's not the proper way. In order to delete the list, I need to go traverse, and while traversing, I need to come to each node and say, hey current, preserve next, delete yourself. Now I go to the preserved next. Hey current, preserve next, delete. Now I go to the next. Hey current, preserve next, then delete. So while traversing, I need to preserve current next. then delete current. So I go to the destructor. Here's my destructor. I'm gonna say I need a current pointer, node star L current node equals to mhead. And I need to preserve L next node. In this, at the beginning, it's null. Then I'm gonna say, hey, are we dealing with an empty? If it's empty, no need to release an empty. Otherwise, now that I returned, I can just write the code. I don't need an else, because this code is not gonna be reached if this gets executed. So I don't need if else. I'm gonna say while L current node, while this is a valid node, I need L next node to be equal to L current nodes next. I need to preserve next, then I need to delete L current node. Now that I'm done with this, I need L current node, because this is my condition. So I need L current node to be in L next node. While M node is not equal to null, yep, L next node preserve next, delete current, then tell it that you are now next. So this destructor will be called once main reaches this scope, or I can trigger it myself. I can say list dot linked list. So here will be destroyed. So F11, what is mhead? It's 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5, and null. So I'm gonna say give me current node, and next node is null. Are we dealing with an empty list? No. Okay. While current node, which is now equal to head, so while current node, give me its next. Notice its next, it is the value 2. So now that I have next node, which is 2, that points to other ones, I'm gonna delete current node. By deleting current node, I also deleted mhead. Now that I deleted mhead, or the first node, I'm gonna tell current node to become 2. So the node with 2. Current node has been deleted. So now current node is the node with the value 2 that points to other ones. So again, hey current node, are you valid? Yes, I'm valid. Then give me your next, release yourself, move on. Hey current node, you're now at 3. So let's pin this value. Give me your next, delete yourself. Now you are 4. Are you valid? Yes, delete yourself. Now you are at 5. Give me your next. Now next is null. Delete current, which is the last node. Now current becomes null. Now that current becomes null, I'm gonna break out of the loop when I already deleted all the nodes. And this is the right way to delete an entire linked list. These operations are very important, very, very important, especially in the test. So study well. Test is soon. It's gonna be Friday, Saturday, Sunday, or Thursday, Friday, Saturday, we'll see. And it's gonna include everything we covered from midterm till today. And good luck. Actually, before I finish, I'm gonna send it as an email. Never mind.